Welcome to our community service series in How Computers Work. I'm Elder Stanley, a missionary for the Church of Jesus Christ of Latter-day Saints.
Hi, I'm Austin Kellum. I'm a student of Elder Stanley here.
This time we're discussing how a CPU works. So let's get started with how a CPU works. The Central Processing Unit, or CPU, is the brains of a personal computer. It's a digital microelectronic device that contains, in the case of a real world, billions of transistors. Your i7 processor would have in excess of 3 billion transistors, all on one small chip. David Patterson, who's the author of one of the textbooks that I used when I taught this class in school, says that a CPU is a data path and a control circuitry. When I first read that, I thought, man, what's this guy talking about? But after having built some, it is a good definition. What we need to do is we need to move data around from various parts of the central processing unit, and there has to be some kind of control that makes that happen. It includes storage elements like registers and combinational logic. What happens in a CPU is we load instructions from a memory and accomplish those instructions. We take the instructions, we do what's defined by that instruction in that central processing unit. Here's a simple central processing unit architecture. In this architecture we have a device called an accumulator. It's where we store a number that we're working with. We have an arithmetic logic unit. It's our adder that we did before. It can add two numbers. The accumulator and the memory data buffer take the results and put it back in the accumulator. We have a control part of the CPU. One of the devices is the program counter that keeps track of what instruction in memory we're running next. And then we have an instruction register that allows us to decode that instruction. We have buses that bring data back and forth between the memory and the ALU. The important ones are the address that goes in, that tells the memory where to read or write something from, and then the actual data that's read or are written to the memory. It's also important for a processor to talk to the outside world. If it doesn't talk to the outside world, it's not very useful. You can't see it do anything. So we want to be able to bring data into the processor. We want to be able to send data out from the processor. In our simple computer architecture that we're going to work with today, we'll see that that computer is designed to have 4 instructions. I usually ask my students, how many of you have built a CPU? And none of them have. They may own one, like your i7, but you didn't design it or build it. I didn't build an i7, but I have designed a little 4 instruction computer. An i7 will have hundreds and hundreds of instructions, and that makes for a very complicated machine language and to try to understand what's going on inside the processor. In this case, I've designed it very simply to have only 4 instructions to make it so that it's easier to understand what's going on inside the computer. Those instructions include a load instruction that will take something from the memory and put it into the accumulator. We have an instruction that's called a save instruction that will take what's in the accumulator, write it into the memory. We have an add command that will take something from memory and add it to what's in the accumulator, put the results in the accumulator. And then we have a jump conditional command which will change the flow of the execution of the program by taking a value from an instruction and putting it in the program counter. So that will tell us to start from a different location in the memory to run the program. We only have 4 instructions, but we also need to do input and output. So what I've done is I've reused our store and load commands to do input and output. If I say load from the highest value that I have in my computer, it will actually load from a keyboard. If I say store to the very highest address, it won't actually go to the memory, it will go to the output display. So those are the architecture of my little 4-instruction computer. This is what this computer looks like. This is probably the most complicated of the 4 sections of our lesson, because this is a fairly detailed little computer, even though it's much simpler than a real-world computer. We will find that we can break it up into chunks, and we'll look at the individual chunks that make up this processor. Just for chuckles and grins, let's look at how it actually works. What we're going to do is put a program into the computer memory. So we'll load a program. This is one that draws little pictures on the screen and lets us, anyway, it's not a real complicated program, but it's a illustration of how this computer actually works. So we'll enable the clock, and we'll turn on the display here. And now you can see here it says box, circle, or triangle. We can enable the keyboard and press a T for triangle, and we'll see a triangle being drawn on the screen. If we push a B for box, we'll see a box. If we push C for circle, then we'll see a little circle. So anyway, this is just showing this 4-instruction computer working. This is what we're going to try to understand in this lesson today. One of the first parts is the address subsystem. What the address subsystem does is creates an address for the address bus to go into the memory to tell us one of 2 things. We'll either tell it what program instruction we want to run next. If that's happening, we'll get the address from the program counter. Or if we're using an address in an instruction, for example, getting something from memory, putting something in memory, changing the program counter, adding something from memory, we'll get that address from what we call the instruction register, and we'll see that when we talk about the decode module of this computer. Anyway, so this is the address subsystem. We'll either send an address from the program counter for the next instruction to run, or data from the instruction register that will give us a memory location to use in a command. So this is the memory subsystem. It takes an address in, and then we have a command to write to the memory, or we can read from the memory. Data comes in or out through the data bus, and this controls whether we're reading or writing. Let's look at the next subsystem. This is the accumulator and arithmetic logic unit, part of this computer. If we look at the computer itself, here was our address subsystem up here, and then our memory subsystem. Here's this accumulator system down here that we're talking about right now. It has an adder. This is just like the adder we built when we looked at the individual logic circuits. We saw how we could build an adder. In this case, it's not a 4-bit one, it's a 10-bit one, because this computer uses 10 bits of address. Here's the accumulator. That's the only place in this computer where we can work with a number. We can bring something from memory, put it in the accumulator. We can take what's in the accumulator, put it in memory. We can bring a value from memory, put it into the data buffer, add it to the accumulator, put the results into the accumulator. And then the one last command we're going to see is we're going to see one where we change the location we're going to run from memory, which means we have to update that program counter. When we update the program counter, we update the program counter from the address that we'll see in that instruction decoder. And in that case, we only jump to that new address if the accumulator is not 0. If there's a 0 in the accumulator, we'll ignore that instruction. That lets us do logic tests inside our program. Okay, here's the keyboard module. What it does is reads from a keyboard if the address is this highest address, FF. So if we select the address and the memory at the same time, we'll read that value onto the data bus and put it into the accumulator. What happens first when we do the read command, read subsystem, is the first thing that happens when we press when we give a command that says read a character, is the computer will stop the clock, and then it will wait, and as soon as we press a key, that reset clock will start the computer clock ticking again. So when we tell it we want to read the keyboard, we'll stop the computer until we press a key. We also use that to pause the computer if we want to have a pause command. This is the output subsystem. So what it does is takes a value from the data bus and sends it to the display. If the address is FF and we're writing to the memory, we also put a box here so we can clear that terminal if we want and run another program. So what this does is sends the contents of the accumulator to the display device when the address is 8 ones or FF. Okay, here's the instruction decoder. Talked about how the instruction decoder is really important. What this does is part of the control system of a computer. The first thing we do when we get an instruction from memory that we're trying to run, we'll put it into the instruction register, and then we'll split it into two parts. We'll split it into we call it an operation code. This is a number from 0 to 3, which tells us which of those 3 instructions we're going to run. And then we have an address up here, and this tells us where we get whatever we're working on. So for example, if we load something from memory, 01 would be a load command. That would be the address we'd load from. In this case, since that's 1111, it would load from the keyboard instead of from the memory. But for any other address, we would actually get a value from memory and put it into the accumulator. So that's called the instruction decoder. It splits the instruction into two parts, an operation and an address. This is the part that actually makes the computer automated. What this does, remember we talked about how Dave Patterson in his book on computers said a computer is a data path and control circuitry. The parts we've been talking about are the data path. This is the control circuitry. What the control circuitry does is it takes in a clock pulse and it takes in an operation code, and then it hooks various parts up to the computer, to other parts of the computer to make the instruction happen. For example, the first thing we need to do is bring a character from the program counter, the address in the program counter, into the memory address. So what we would do is we'd select the program counter, and then we would write to the memory address register, and that would put an address in the memory address register for the instruction we're going to get. We'll see how this works a little bit more later on to make all of our instructions possible. But what this does, each instruction is not just one command. If we do an add, the computer doesn't instantaneously add. We'll see that there are steps that have to happen. And this is the thing that sequences those steps to make it happen. When you look at a really complicated processor like your i7, the instructions will have maybe 17 steps or something like that. It will actually have many instructions going on at the same time. So it'll start working on part of one of the instructions, and then while it's finishing that instruction, it'll start working on the next instruction, and while it's finishing that one, it'll start a third one. That's a little bit of a problem. It makes these computer processors really complex, because if I start working on an instruction, and it turns out that I'm not going to actually do that instruction because the previous instruction says jump to another memory location or something like that, then I have to kind of flush away those previous parts of instruction processing and start again. So there's a lot of really sophisticated stuff. My little processor doesn't do that. But anyway, we'll talk about the steps of an instruction here. So this is an example. Suppose you want to do an add instruction. These are the steps that have to happen for an add instruction to occur. The first thing that has to happen is the program counter value, the instruction of the instruction we're about to run, needs to be loaded into the memory address register, and then that memory address is applied to the memory, we grab the character that's in memory at that location, and we put it into the instruction register. And then we also have to add 1 to the program counter so that we're going to do the next instruction when we finish this one. We take that address that's in the instruction register, the address part, and we move it to the memory address register. We grab the memory content at that location and put it in the memory buffer register. And then we use that accumulator, adder, to add the memory buffer register to the accumulator, and we put the results back in the accumulator. And then we're done with that instruction. So it's not just one step. We have to do each of those things one by one. And so that's what that instruction decoder does, is it takes that instruction and implements each of the individual parts. So this is a really small program. Let's actually come in here and look at what's in memory. So we'll see, it's just, I don't know if we can zoom in on that with their camera, but in here, what you see in here are the instructions the computer sees. So the first instruction is this 1FF. That's an instruction to read from the keyboard. So we're going to read a character. We'll put it into the accumulator. That's what the 1FF does. The 2FF says take that character that's in the accumulator, put it in the display. Then the next instruction says add what's in memory location 5. So we'll see over here in memory location 5, we've got a 20. We're going to add a hexadecimal 20 to that character. It turns out 20 is the difference between uppercase A and a lowercase a, for example, or a uppercase Z and a lowercase z. So we add 20 to a number and it becomes a lowercase number. And then we have another 2FF that says display that character. And then we've got a 300 that says jump. The address we want to jump to is the very first address, so we'll start over and do that again. So we'll get uppercase characters from the keyboard, display lowercase characters. Let's clear the terminal so we can see this when it runs. And let's run this. So we typed in an uppercase A, and now what we see is a lowercase a. If we type in uppercase Z, what we'll see is a lowercase z. So just a simple little program. Let's slow down this clock so that we can kind of watch it go through the individual steps. So instead of clocking at 1,000 times a second, let's have it go once a second. So now you see this clock going tick, 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 tick. We'll tell this, we'll just do another character here. Let's put in a capital B. So we'll see.
Oh, you don't.
So now it's just going through really slow, going through the individual steps. This counter here shows you what part of the instruction we're on. I mean, what step we are in the individual instruction. Each instruction is going to have maybe 3 or 4 or 5 instructions. That was the add command, has 5 steps. Now we've got to load into the display command. That's more like 4 steps. So we see the lowercase b. And now we're going to see the program counter has been at 4. It's going to reset the program counter to 0. That's what that jump command does, is jumps to 0. And then here in just a second, we'll pause. We're pausing right now for another keyboard input. What should we try?
Try letter C.
Letter C, okay. So you can see the individual steps happening. So we get an address, in this case FF, that means that we're getting a character from the keyboard. Now we're in instruction 2. Instruction 2 is the one where we display the character. Now we're in instruction 3. This is where we do the add, lowercase c. Now we've got this 3 command, so we reset the program counter back to 0. So that's what's happening inside this little computer. I don't know if that feels like overwhelmingly complex, but
yeah, it's pretty complex for anyone out there watching.
Yeah, it is pretty complex. Let's load one more program into here. So we'll clear the terminal and let's load a program. We'll load one that does a little bit of add two numbers. But anyway, lowercase c plus 1 is lowercase d. That's not the kind of math we were really thinking of, but let's put in a 1 plus 2. 1 plus 2 equals 3.
Perfect.
Yeah.
3.
So this little computer can do stuff like that. One of the things that I think is kind of important to note is that you change the contents of memory, you change what this processor does. It's called a von Neumann architecture. What that means is in the memory we have not only instructions, but we also have data. For example, in this case we have the 4 instructions that we gave it to get a character, display the character, add 20 to the character, display the character. I guess we had 5 instructions, and then jump back to the beginning. But then we also had to put in memory someplace that 20. And that 20 is not an instruction, but it's data.
Okay.
And it's really key in memory. So anyway, so those are some examples of instructions for the computer. And this computer, let's go back to our PowerPoint presentation and see what else we got. Okay, next time what we're going to do is we're going to talk about machine language programs for this simple computer. When we do that, we're going to use not my Terry
Super
Logic
big.
computer.
Yeah, super
We'll
big,
try to
complex.
make it simpler by just using an emulator for my computer. This was actually made by one of my students. He wrote it in C#, an emulator that takes exactly the same memory images and then runs them. Let's look at this emulator for just a second. But anyway, this is what we're going to use next time. So we'll go here to our virtual machine. This is this virtual machine that my student built. Let's load a memory image. So let's load one. Let's load this formatted add two numbers demo that we were just doing. So here's the program in memory over here, the instructions. We can single step through this program and see what happens. So we'll do the first step. It says get a character from the input. So let's put in number 1. And now it's waiting for the next step. The next step says write that character to the display. And then we're going to add, well, let's see what this means. We're actually adding the thing that's down here in memory location 11 to that number that we just put in. What that does is converts it from a character into a number. We'll talk about that more next time. And then we're going to save it into a memory location 15. So we should see that number right here. So now there's a 1 there in memory. That's that character that we typed in, converted into a number. And then we can keep stepping down through here. We're going to display character. The character we're going to display is a plus sign. We're going to ask for another input. Let's put in a 2 now. So we've typed in a character 2. Notice that in the accumulators of 32, that's the character 2, not the number 2. What we're going to need to do is add to that character 2 our other number. So we're going to add from memory location 15, the number that we had before. And now we've got a 33. That's the character for 3. We'll see that. Oh man, we're out of time, I guess. We'll go through here anyway. This is what we'll use next time. So we're talking about computer programming languages next time. Thank you for your attention.
Thank you. Bye.